All right, and we're recording. And today, at the day of recording, is National Candy Day. Is that what we said?
National Candy Day, according to the internet.
According to the internet. Well, the internet's right, always. 100% of the time.
I don't think that's true.
Show me a counterexample.
Where to begin?
Where to begin? No looking at Wikipedia, that doesn't count. So we have prepared ourselves with our favorite candy, and it may or may not actually be our favorite candy. Mrs. Contreras, what did you bring?
Man, now I can't. So I brought gum because I'm an adult. But this is my favorite kind of gum. This is my, I'm in the car and I need to be awake gum. This is my, I need to think about math really intensely gum. Because one of my study buddy in college, she started chewing this gum because of her, dentist told her to. But then it became, the gum that I associated with doing math homework. So this is, proofwriting gum in my mind.
I like that. That is there's so many little things in our life have connections to such completely different things.
Yep.
Right,
but
my
actual
candy is
favorite
not
candy,
that.
Though, I feel like I need to redeem myself.
Mm-hmm.
My actual favorite candy is Sour Patch Kids, particularly the red ones. But I'm an adult, so I don't keep that in the apartment.
Before we continue, I have some questions. Sour Patch Kids. Each color is a different flavor?
Yes.
How about Skittles?
I have no idea.
M&M's, the color does not affect the flavor, right?
Mm-hmm.
All right, I'm segueing into my favorite candy, by the way.
Oh, okay.
All right, how about Reese's Pieces?
I think they're all the same.
Yeah, they're definitely all the same. Reese's, so I call them Reese's Pieces. I just said Reese's Pieces to be I guess politically correct. Reese's Pieces, but I call them Reese's. This is a political issue. Reese's Pieces. How does that make you feel?
I mean, you can say it however you want to. I say a bunch of things really weird. I say museum instead of museum. I grew up in the South, and so just a little bit of twang comes out sometimes.
Well, I used to work in this theater, and we would constantly, my coworkers and I would constantly come up with these concepts that would spark outrage, such as the sandwich debate. Is a hot dog a sandwich? And one of the things is, how do you say this candy? And I guess the smart people were like, it's Reese's Pieces, because that is how you pronounce Reese's, and that is the word pieces. But I say Reese's Pieces.
I wonder if the people at Reese's Pieces, the people who make it, is it Nestle or something? I wonder if they're pleased that you're making their branded name.
It's Hershey. It's Hershey, by the way.
Oh, it's Hershey? Okay.
Yeah.
Making their brand name something different from what the English language does. Like Fruit Loops, do you think they're happy that they have changed the word fruit?
Wait, I'm not understanding. They have changed the word fruit?
Isn't it fruit? F-R-O-O-T? Didn't they?
Oh my God, you're right.
They do? Wait,
I think you're right.
Yeah, F-R-O-O-T. That's what they do for Fruit Loops. This is not Vieta's formula.
So we're going to be doing Vieta's formulas very soon. Oh my God.
Right?
That's awful. Now I'm mad at myself for changing Reese's Pieces to Reese's Pieces. This is worse. This is worse, I think, objectively. Back to what we're going to do.
Objectively, that's worse. Yeah.
Sure. Reese's are actually my favorite candy, but I wanted something that I could munch on. So I got Reese's Pieces.
But now all the students are going to be really hungry while they're watching this video because they're
go ahead and eat. There's no food rules. There's no food rules at home.
But what if there totally are food rules at home, Mr. Kirk?
Well, they're watching our videos. They can eat and munch on whatever they want.
But maybe their parents don't let them eat in front of the computer.
That's fair, yeah. Yeah. All right, fine. Well, if you're allowed to eat in front of your computer, don't eat during class. But if you're allowed to eat in front of your computer while you're watching a video, feel free to, especially if you have some Reese's Pieces or gum, go ahead and enjoy that. While we get into, I believe I'm sharing my screen. Cool.
You are.
Vieta's formulas. This is very like abstract dissection of the quadratic equation and polynomials. Not something that you would normally do in a, I guess, your like standard American class, math class. But we're gonna do it because I think they're cool.
Standard U.S. American class.
Yeah. Thank you.
Like maybe they do it in Canada. Who knows?
That's true. Yeah. Yeah. All right. So let's do this. Let's get Vieta's formulas. We're gonna generate them slowly but surely. So my question to you, Mrs. Contreras, is find the sum and the product of the roots of this function.
Well, that's really nice because I think that is factorable. And if we can factor that, then we can find the roots really easily. And then we just take those numbers and add them together to find the sum and multiply them to get the product.
So let's see. Factor, I see a 7 and a, no.
I think
5 and a 3?
5 and a 3.
X plus 5, x minus 3. Roots are -5 and I want to write a 2 there, a 3. So what's the sum and product?
The sum is -2 and the product is -15. Wild. Those are the coefficients for, well, that's the coefficient for x, and then that's the constant term, the product.
The product is -15. Sweet. So negative
of
the negative flipped, but for the other one, the product, it didn't flip. That kind of makes sense though, because when we when we expand x minus r1 and x minus r2, we get x squared plus, right? No, minus r1 plus r2 times x plus r1 times r2, like that. We did that a while ago with a and b. Now it's just r1 and r2 because we're using that word now, roots. Because maybe there's a connection between the sum and the product of roots and the coefficients. Let's look at this one that hopefully is also factorable.
This one is more of a big brain problem, huh?
Big brain time.
Big brain. I didn't understand that until like my students explained it to me last year.
What is it?
It's like when you're really trying hard and you think of something like after using all of your brain, like really thinking hard about it. So then it's like a big brain thing.
Big brain moment. That makes sense to me. All right, big brain time.
Big brain.
Well, let's use all your brain to solve this.
Okay, so we got 3 as a. So we have the factors of 3 are 1 and 3, and then 3 and 1, because it's easier to flip than 10, which has more factors because it's not prime. 1, 10, and 2, 5. And
no flippy floppy. We need to get to 13.
I think
I see it.
Yeah.
I think it's this first one, right?
3,
10 and 3. Yeah. So we're gonna have a 1 and a 1 x plus. Oh, not plus, because we got that minus 10 there. I'm just write x and 1, and I'm gonna write 3 and 10, and then we'll worry about those signs.
So then we need, wait.
Oh.
No.
Do we have the incorrect choice?
I think so.
This happens every now and then. Let's backtrack.
Okay.
Get rid of that. Get rid of that. How about 3 and 1 and 2 and 5?
Yeah.
That's gonna get us the other way around. That's gonna give us the 15 and the minus 2. Right, that happens sometimes. 3x and 2. And 1 and 5. And then now, hopefully, we can factor it. Let's see.
So we have 3x plus 2.
Oh, I think we want it to be plus 5, right?
Minus 2. Plus 5.
Big brain.
Yeah, big brain.
We just used all of our brains. So everyone was looking at us like, we did that 2 minutes ago. All right, wait, what are the roots? What are the roots?
The roots are -5 and 2/3.
2/3, cool. And then, so what's the sum and product?
The sum is, well, -5 in thirds is -15 thirds, plus 2/3 is 13 thirds.
Okay.
And
Okay.
Product is negative 10 thirds.
It's a little bit easier. Is there a relationship between the sum and the product of roots and the coefficients?
Well, the product is just the constant term, negative 10, over the leading term, a.
Okay.
3. And it looks like the negative 13, that's the negative of our b, the constant, the coefficient for x, and then 3 again is a.
I think we can hypothesize something. I think we can make a conjecture, to throw some big brain math terms out there. They're going to hate us for saying big brain so many times.
Maybe that's the theme.
Yeah. Wait.
Oh yeah, we can just be as annoying as possible. That's the goal.
That's how I live my life. All right.
Yep. It's lit.
Conjecture. The sum of the roots in a quadratic is the opposite of the second term divided by the first term. The product of the roots is going to be the third term, the constant term, not opposite. We do have a negative here, but there's a negative in the original function, divided by the leading term's coefficient. Let's prove or disprove this conjecture. This is our conjecture here. Suppose that ax squared plus bx plus c is equal to 0 has two real solutions, r1 and r2. In other words, ax squared plus bx plus c is equal to 0 is true if and only if x is equal to r1 and x equals to r2. What do we know about ax squared plus bx plus c then? If we know its roots.
Then we know it's factorable.
Okay. So what is a factor to?
A times x minus r1, x minus r2.
Boom. How can we now relate r1 and r2 to the original coefficients?
Well, can we like multiply it out?
Let's do it. We kind of did that up at the top. Over here, but we'll do it again more slowly this time. A times x, x squared. Negative r1 times x, negative r1x. X times negative r2, negative r2x. And then negative r1 times negative r2, positive r1, r2.
And then there's that a. Can you distribute that everywhere?
Yeah, ax squared minus r1ax minus r2ax plus ar1, r2. Can we do something with those two middle terms?
Can we combine like terms?
Let's combine like terms. I'm thinking like GCF, but what we're saying is the same thing. Or we want to combine like terms. These both terms are x terms, so we're going to have an x, and then we're going to have a minus. I guess I could do like a plus here. A minus r1a plus minus r2a. Mm-hmm. Can you like help me make sure I'm right?
I think that's good.
Or maybe I could
do a minus out front.
Minus out front. I think that's going to look cleaner. Minus r1a plus r2a.
Okay.
And then we have a plus a r1, r2. Cool. We're trying to verify that the sum and the product of the roots are what we claim them to be, negative b over a and c over a, respectively. All right, how can I relate the roots with the original coefficients?
Well, we have the original coefficients of b, and you can just see if that's going to be.
Let me get some more colors.
We have like a b down there. Yeah.
Like b is like the fact that these two things are equivalent says that b is equal to negative R1A plus R2A. Oh, sorry, negative R1A plus R2A.
Mm-hmm.
Let's just
And
solve
then-
this one.
Okay. So I guess we can factor out an A from the right side and then divide. We can divide by negative A.
Divide by negative A.
Mm-hmm.
We get R1 plus R2 is equal to B over negative A.
And that funky arrow that you drew, Mr. Kirk, that's implies, right?
Mm-hmm. And I could also, because both of these are, it's bidirectional. I haven't done anything that is not irreversible, like squaring. So I could put an arrow on both sides. It's a way to imply something without using the equal sign. I like to be careful how I use my equals because equal has a very powerful meaning. All right, so I think we just showed it, right? Because this negative can float around anywhere.
Mm-hmm.
I'll put it on the top just because that was our conjecture. The sum of the roots is negative B over A. How about the product of the roots? Let's go with Kermit the Frog green.
For Sesame Street Day.
Yeah, Sesame Street Day is coming up soon.
So
for those who care.
We have C that we can just set equal to our constant term A, R1, R2.
And I think this one's real quick.
Yeah, divide by A.
And it's not opposite. It's just boom, C over A. Okay. This is the first of what I am calling Vieta's formulas. This is the first. But there's an S there. There are more. Right? But
well, that was two formulas. So
yeah, I guess, yeah, you're right. Yeah, so we have two of the, which you'll learn there to be an infinite amount of formulas. Right? But the product of the roots of, right now, just a quadratic is C over A. And the sum of the roots of a quadratic is negative B over A. Let's utilize it.
I wonder if any students got bothered because you didn't write your name on the top of the paper.
Oh, no. Well, that's just not allowed. How will you know that it's my work? It is today, and it is a natural number. Last time I did integer. All right, down here. All right. F is a quadratic with rational coefficients. And f of 5 minus root 13 over 6 is equal to 0. Find the other root of f, then find a possible rule for f. Huh. I feel like we haven't been given a lot of information.
It really doesn't feel like it's enough.
Yeah. Huh. Well, there's a really important word in this problem. It says, it starts with an R.
Does it end in ational?
It ends in ational. Starts with an R, ends in ational, and it's not respiratory national.
Okay.
It's not respiratory. That's not in the sentence though. Right? It's this word right here, rational. That was a terrible, terrible, terrible joke. I take it back.
No,
I never said
it's in the video forever.
No. All right, so, and you know it's me because I just put my name on the assignment. All right, F is a quadratic with rational coefficients. All right. If I have two roots.
That root is irrational.
That root is totally irrational. And if I have x minus r1, and I have x minus r2, and we've established now several times that this expanded is x squared minus r1 plus r2 times x plus r1 r2. We've established several times now that this is our expanded form. Give me 1 second for this really loud motorcycle or car that needs a muffler to go by. Cool. I need, if the coefficients are rational, I need another root that when I add to 5 minus root 13 over 6, I get a rational number. And I need another, the second root to also satisfy when I take the product of the two roots, I get a rational number. So one of our roots is 5 minus root 13 over 6. I need a single root that satisfies both these conditions. Can you think of a number that does this?
I think we need to conjugate.
That's like the verb of the day. We need to conjugate. Not congregate. Not promulgate. But conjugate. I'm going to stop with my terrible word humor. Okay, so we're going to conjugate this thing. All right, what does that mean? What does that mean?
Well, in like in your language classes, when you're conjugating, at least in Romance languages, you change the ending, right?
So we got. I'm gonna write this as 5/6 minus root 13 over 6. You're actually teaching me something valid, right now. Right? Yeah.
Yeah. So
I never thought about the origin of this word.
Oh, that's just how I remember it. I don't know if that's like actually the connection.
Oh, I bet you it is. People that are into etymology, the history of words, look it up for us. Write about it in your journal. We'll learn through you. So let's change the ending. 5/6 plus root 13 over 6. Cool. That's what it means to conjugate. And you know what? I'm going to go back to the single one just because I wanted to make it clear that the 6 is still there. Plus. I think this is going to do it. All right. Let's confirm that it does. What is R1 plus R2?
10/6 or 5 thirds.
Let me actually write that. Yeah, so it's going to be 5/6 minus this thing plus 5/6 plus this thing. Those are going to cancel. We're going to get our 10/6. Cool. We have rationalized our roots, one could say. What's the product?
Product is slightly trickier. So we have 5/6 minus. Oh, okay, we're gonna do it like that. That's cool.
Well, I think we have like an advantage here, right? Something we learned a while ago.
Super denominator killer.
Kind of. Difference of squares, right?
Oh, difference of squares.
Difference of squares.
So
25 over
30.
23.
Wait, 25/36 minus 13/36.
It's gonna be 12/36.
Which is 1/3.
1/3. Cool. All right, we have found another root that does at least what we set out to do. Is it the other root? We don't know that yet. But we have found a root that does rationalize our coefficients. That's good. And I think it's time to just make the statement. Do you know what that statement is, Mrs. Contreras?
No.
Irrational roots come in conjugate pairs. Conjugate pairs. Always and forever. We're not going to do a proof here, everyone. But I do have an assignment that I could send to Mrs. Contreras and we could send out to everyone to do for fun as like a bonus. Maybe do that problem in your journal as your journal entry. But I have a guided proof to prove that irrational roots come in pairs, and their pair is their conjugate. Right? That is always the case. Right? If I give you an irrational root, you implicitly know a second root 100% of the time. And there's a mathematical proof that shows this. All right, so f is a quadratic with rational coefficients. One of our roots is 5 minus root 13 over 6. Implicitly, we know that 5 plus root 13 over 6 is another root. Let's find a possible rule for f. I'll change up my color.
Well, we have the sum is 10/6, which I guess we could also write as 5/3.
5/3. Oh.
So now we have the same denominator 3, which could be our a.
Let's set a be 3.
And then I need to sneeze, so I'm just gonna. I did not need to sneeze, but
the sneeze lied to you, like it does so often. The most untrustworthy. Anyways,
so we have a is 3, and then for c, that's going to be 1. And
you look at the product of the roots. Got it.
And then b is going to be the opposite of 5, which is -5.
Boom. So I think we got it. F of x. Here's a possible solution. 3x squared minus 5x plus 1. I think another one could have been, hey, instead of simplifying 10/6, maybe we write 1/3 as 2/6, and then do the exact same process you did, and I believe we would have gotten 6x squared minus 10x plus 2.
Which only differs by some vertical dilation.
Yeah, that A that keeps popping up when we do our proofs. Sum and product of roots at work. Vieta's formulas at work. If given a root, and maybe some other constraints, we can generate functions. We can take functions and find the roots. Work both ways. Let's think about the roots of quadratic equations. When
Can we
are
write down the quadratic formula?
I think so.
I think that would help me process this.
Yeah. So we got the solutions to the roots of this are negative b plus or minus the square root of b squared minus 4ac all divided by 2a. All right.
And I do sing it in my head every time.
I do not. My pen is struggling.
It's upset that you're not singing it.
4ac all over. It knows. All right. So when do we have irrational roots? When do we have rational roots? And when do we have the multiplicity of 2? We don't have to do these in order, but what are you thinking?
I think I want to start from the bottom because that seems like the simplest. When are we going to have a double?
Okay, when are we going to have a double root?
When that plus or minus is 0.
Yeah, right, because
negative b plus or minus 0.
Negative b plus 0 divided by 2a and negative b minus 0 divided by 2a are equal, and you're going to get that double root. So we have a name for that thing under the square root.
Discriminant.
I think it's ANT, discriminant. Discriminant, though. And when the discriminant is 0, so let me just actually say this. The discriminant is b squared minus 4ac for a quadratic. You'll see the word discriminant pop up all over different topics of math. And its definition changes a little bit here and there, but there's a really cool connection that comes together in the future. But the discriminant is that, and when the discriminant is 0, double root. Cool. This is for quadratics. When's it going to be irrational? Or do you want to jump to the first one?
I think irrational. That's a good one.
Winter is coming.
Winter is coming. Hang on.
When you sneeze, I get to eat my Reese's Pieces. All right, wait. What would you just say? You want to do irrational or rational?
Irrational, because I feel like just going in order is nice now.
Okay, so when are the roots going to be irrational? When will they come in pairs?
I think that's whenever in our discriminant we're not getting like something rational or something that's a perfect square.
So when b squared minus 4ac does not equal, or I could do this, when b squared minus 4ac is not contained in the set of
n squared
perfect squares. But I think there's another little nuance that we need to say. Like I can think of an example that's not a perfect square that would give you rational roots. Because like, is 4/9 a perfect square? I feel like the definition of a perfect square, I believe, you can correct me if I'm wrong, we can look it up later. I believe it is the square of an integer. Right, so 1, 4, 9, 16, 25, but not 4/9. So I think we can add to this when b squared minus 4ac is not a perfect square or the ratio between perfect squares.
So could we say that as like P over Q quantity squared? Or P squared over Q squared?
I think we could say both, right? When P divided by Q. I'm not really sure what you're getting at.
Well, because like we can think of it as like a ratio that's being squared, or we could have the components like P squared divided by Q squared. So we can think of them as separate perfect squares. Either way is the same,
Yeah.
right?
Mm-hmm. So if that number cannot be squared to become a rational number, then we're going to have irrational roots. Right? There's another proof that you guys can do in your journals, and that is if this is not met, then the square root of that number will be irrational. And then if you take a rational number and you add an irrational number to it, you're irrational. That's the idea here, I think, is we're trying to make sure that this number is irrational. That's when you have irrational roots, when the square root of the number is irrational. When is it rational?
Any other time.
Yeah, b squared minus 4ac is in the set of, I'm lazy, that thing. Right, b squared minus 4ac is in that set. If you get a perfect square or the ratio between perfect squares, then you're going to be rational. And fun fact, if the discriminant is in this set, then the original problem was factorable. So if you're ever like, I'm not sure if this is factorable, look at the discriminant real quick, b squared minus 4ac, and if that is a rational number, you're in business. It is factorable. This is actually my favorite scenario. Maybe the last one, but I like the middle one because of this fact that I want to reiterate. Rational roots come in pairs with their conjugate. And this is one way to think about it. These are the roots of a quadratic. So if a rational root is a root, then that minus or that plus is going to be the other root. It's kind of why that's happening. All right, let's keep going. Let's take this information that we've just absorbed and apply it.
So I see double root. Double root means that our discriminant is 0. B squared minus 4ac equals 0. So let's just plug in what we know.
Let's do it.
B is 2 times k plus 2. So when we square that, we get something else. Minus 4a is 1, and c is 9k.
Cool.
And that equals 0. This looks sneakily like another quadratic. Wow.
All right, so k plus 2 squared times 2 squared. Let's distribute that exponent rules.
Okay.
And you have 4 times k squared plus 4k plus 4.
Sounds good.
Cool. 36k?
Yep.
K squared?
Very integrally.
It does. Plus 16, not 116.
116.
That's not how math works. Plus
Wait,
16.
you did it again.
How did I do it again? What? 16k. I got it.
Okay.
Plus 16 minus 36k equals 0.
All right.
All right, let's just keep going.
Combine some more terms. So we got minus 20k.
Minus 20k. 4k squared minus 20k plus 16. What should we do?
GCF.
GCF.
4.
4 minus
5k.
5k plus 4.
Ooh.
Oh, it was already at 2 answers. Distinct factors. I could get rid of that 4. I could divide both sides by 4, but I don't feel like it. We got a minus 4 and a minus 1.
Yep. Okay.
Okay. I've been waiting to make that joke. And then so k is equal to 4 and k is equal to 1. We're done?
Yeah, we had to find.
I think so, yeah. Yeah, we find k.
Question.
Yeah. All right. Let's just confirm though. Let's plug these things back in. X squared plus 4 plus 2 is 6 times 2 is 12 plus 36. That totally has a double root. That's a perfect square trinomial.
Perfect square trinomial with x plus 6.
And then what am I going to get if I plug in 1?
1 plus 2 is 3 times 2 is 6. And 1 times 9 is 9. Perfect square trinomial. X plus 3 squared.
Nice. Cool.
We did it.
All right. So once again, reiterating, we are looking at how to monopolize our understanding of roots to better understand. I mean, these are all convoluted problems that don't really, tell us too much about like reality, but knowing this property of roots might be beneficial later. How about cubics? We've been doing this for quadratics, but I claimed earlier that there were multiple Vieta's formulas. How are we going to establish Vieta's formulas for a cubic?
I think we should multiply out the second form to derive the cubic form of the sum and product of roots formula.
All right, let's do this as fast as possible, because this is a little bit of we have angered the algebra gods. A times x minus r1 times x minus r2 times x minus r3. Right, this is the factored form of our arbitrary quadratic. We want to look at the relationship between the coefficients with the original coefficients a, b, c, and d. A times x.
And we know that, right? Because we did that before.
And I believe we're going to go with r1 plus r2 times x plus r1, r2. This should be a 3, by the way.
Yep.
X minus r3. Cool. Let's expand this a little bit further. Leave that a on the outside for now. X times x squared is x cubed. X times, that's going to be r1 plus r2 times x squared plus r1, r2, x. That's when I distribute the x to the 3 terms. 1, 2, 3.
Okay.
2, 2, 2. And then if I distribute the negative r3 to each term, I'm going to get a minus x squared r3, but I want to write my r's in the front. That's if I distribute it there. If I distribute it here, I'm going to get a plus r1 plus r2 times r3x. Well, I think I'm going to have just enough room. And then if I distribute the negative r3 here, I'm going to get a minus r1, r2, r3. Let's combine terms.
All right.
I need you to help me with this.
So we got x cubed.
X cubed.
All right, your turn.
Ah, you're the worst. All right, so let me pull up another color. This is an x squared term. This is an x squared term. Those are the only two. So I have a negative r1 plus r2 x squared and a negative r1 plus r2 times x squared minus r3 x squared. I can factor out an x squared and get
and a negative.
And a negative. So negative x squared r1 plus r2 plus r3. Hey, look, the sum of roots.
Whoa. On the second
Negative r1 plus r2 plus r3 times x squared. All right, your turn.
Okay. And then r1 times r2. And that's going to combine with r1 plus r2 times r3 times x. So we get r1, r2 plus r1 times r3 plus r2 times r3, which is, I think, all the different multiplication combos that we can have.
Boom. Some permutations.
Mm-hmm.
And is that a plus or a minus?
That is a plus.
Nice. And then I got the last one. R1, R2, R3. Boom.
And it's a minus on that, huh?
Mm-hmm. It's a minus on that one. And can you think of a good, like, quick way to think about remembering that it's a minus on the last one?
Well, we have an odd number of roots, right? And so if we're subtracting So the sign on the roots is going to be like negative. So we have -1 to the power of however many roots we have, which is 3. -1 to an odd power is always going to be -1. But then if we think back to like the beginning where we were looking at quadratics, we had 2 roots. So the parity there is even. So -1 to the even power is going to give us a positive.
Boom. What would it be if it was x to the 4th? What if we did this problem again? We're not going to do x to the 4th. I mean, you can if you want, but I'm not doing it. X to the 4th. What's the parity going to be there? What's the last term going to be there?
Well, the parity for is going to be even. It's going to be even because 4 is even. And then we have 4 roots. So -1 to the 4th power is going to be positive. So our last term, our constant term, is going to be plus.
It's going to be like
the product of roots.
-1 to the 4th. R1, R2, R3, R4. I think that's going to be important in a second when you can see down here, we're going to get to the general Vieta's formulas in just a second. If I distribute this A, I'm just going to do that this like lazy way.
Efficient.
Yeah. What are our Vieta's formulas in this problem?
Well, our sum of our roots is going to be...
I'll do this in R1 plus
negative
R2.
Plus R3 isn't negative B over A.
Okay.
What? That's the same.
Wait, so for quadratics and cubics, the sum of the roots is just always negative B over A. Huh. Okay.
Okay.
What is the sum of the product of possible pairs of 2 of the roots? I'm not sure if I said that right, but I think you know what I mean. What is the
C is that over A. Or C over A is that.
Taking all possible combinations of 2 of the roots is going to be C over A. But that's kind of the same thing as in the previous one too, right? Except there's only one combination of 2 when you have 2 roots.
Yeah.
So the product of 2 roots summed is always C over A. What's the product of roots in general here?
It's going to be the negative D over A.
Negative D over A. So the product of the roots is, wait, the last time it was positive C over A. Now it's negative D over A. But that's just
okay. Yeah, because the parity thing, right? That we were talking about with evens giving us -1 to an even power is always going to be positive.
So like if we had that x to the 4th, the product of the roots, R1, R2, R3, R4, would be the last term times a positive 1. So like E over A.
Okay, and E is the coefficient, or E is the constant
term in a x to the 4th. If it was x to the 5th, we could say it's F, but that would be a negative F over A, not a positive F over A, because 5 roots would mean you have a negative. Let's generalize this because that's what Vieta's formulas are. It's the sum and the product of the roots for an arbitrarily large polynomial. So let's give ourselves an arbitrarily large polynomial. I'm going to do that right here. So f of x is equal to A. And let's not use A, B, C, and D this time.
Yeah, it's getting a little much.
Yeah, let's use
A naught.
A naught. Let's use subscripts. A naught, that's like the first one, times x to the, what do you want the power to be?
N to the n power.
Cool. What's the next one going to be?
A sub 1.
A sub 1, x to the
n minus 1.
Plus A sub 2 times x to the n minus 2?
Yep.
This is going to keep happening, right?
Yep.
What's the second to last term?
A sub n minus 1.
A sub n minus 1 times
x to the 1.
X to the 1, yeah. It'd be like n minus 1.
With parentheses, yes.
Yeah, with parentheses, but I'll just put a 1 because I'm, efficient. And then plus the last term, a sub n times x to the 0, or x to the n minus n, or
1.
x to the 0, which is 1. That is an arbitrary degree polynomial. What is the sum of the roots?
Well, the sum of our roots is going to be a sub 1, negative a sub 1 over a naught.
Negative a sub 1 over a naught. It's the second term divided by the first term negated every single time.
Well, the coefficient, not the whole term, right?
Thank you.
Then we'll be left with some x's.
Mm-hmm. And the x's won't cancel. So that is an important distinction. All right, let's get the other easy one. What is the product of the roots?
Well, we need to respect the parity.
Respect the parity. How can we do that?
Negative 1 to some power. But I'm struggling to try to generalize this. What do you think, Mr. Kirk?
I think we should kind of test. So if the power's 2,
then we want that to be positive.
We want it to be positive. So we could square it. So maybe the power, just saying the power, is going to give us the right sign.
Mm-hmm. Because we're working with polynomials. We're not working with crazy functions where the degree, the power, x could be to some rational.
Yeah. This is strictly integer, not integer, but natural number powers. We're dealing with polynomial, not 1 over x or anything like that. No negative exponents. But negative 1 to the n. So if this is a quadratic, I'm going to square. Cool. If it's a 5th power, I'm going to do negative 1 5 times. I'm going to get negative 1. I think that's going to respect the parity. All right. And what is the magnitude? What is the number that's our sign?
The last coefficient, which is our constant term, a sub n, over
times a sub
our
n.
first coefficient, which is a naught.
A naught. A naught. It's like the dad in the Wilbury show, whatever it's called. Do you know what I'm talking about?
No idea.
Wild Thornberries.
Oh.
You know what I'm talking about? Or the dad. Oh, we talked about Disney movies recently in my class. My favorite Disney movie is the Goofy movie, the original. But my second favorite Disney movie, contrary to popular belief that it's the second Goofy movie, it's not. It's Tarzan. Sounds like the dad in Tarzan. Jane's dad? Jane's dad, the really short guy.
Oh, okay.
Yeah,
because I thought Tarzan's dad is definitely not there.
We're here to learn about gorillas. Kerchak. I'm sorry, I'm a really big fan of Tarzan. We'll move on.
I don't think I've seen Tarzan in 10 years.
I watch Tarzan probably once a year, to be honest.
I did that with Lord of the Rings.
Mm-hmm. Well, I do that too, and I do that with Star Wars. I watch Star Wars around Christmas time every year, the holidays. So that's coming up soon. Special? No, I don't. I don't know how to find it.
I think it's on YouTube.
If you can find it, send it to me. We'll put it in the comments below for the viewer. Okay, let's stop wasting time. What is R1 R2 plus R1 R3 plus ... plus R2 R3 plus ... Rn? That's not an R. Do you understand what I'm trying to write here?
Mm-hmm. Yeah.
It's Rn minus 1
of all
times
of the roots, but added together.
Yeah. The possible combinations of 2. What's that going to be?
I'm kind of struggling because is that going to be the second to last? Or is it going to be third?
Let's look back at our previous example. If I take an arbitrarily large polynomial, and then I deconstruct it to its roots, and I expand my x to the n minus, I believe, n minus 2 term is where those products are going to be. In this case, it's this number right here. And it's always positive. And if you think about this with letters, A, B, C, D, E, F, G, H, I, and then whatever. This is why we're not using letters, because we can't go on forever. But if we think about these first 3 with letters, that C term, the third term, is going to be the possible products of 2. So that's going to be C over A, but in our example, that's actually A sub 2 over A naught. Let's do one more and then put a dot, dot, dot. I want you to just conjecture, and then we'll write down the correct one. But what are all the possible combinations of 3 roots? If this was a large polynomial, what do you think that would be?
I think that would be A sub 3 over A naught, and maybe with some funny business with our negatives.
As we move down Vieta's formulas, we are alternating positive, negative. The denominator is always the first term. And this gets to the idea of the rational root theorem. Go ahead and look that up, students, if you are interested. Rational root theorem. Think about that. But we're always divided by A naught, and then we're alternating between negative and positive, and we're going to the next term. These are Vieta's formulas. Boom. These are the two that we care about the most. But these ones may matter if we're trying to utilize Vieta's formulas to our advantage. Let's try to use Vieta's formulas for a cubic instead of talking about the theorem any longer.
All right.
So you'll see in my problem here, polynomial log division is a possibility, but that's not the focus here. You guys have had plenty of opportunities to work on a polynomial log division. How can I utilize Vieta's formulas?
Well, we do know one of our roots because we have f of 4 equals 0. So we know that 4 is a root. And that's really helpful because then we can utilize Vieta's formula.
So we don't know what the other 2 roots are. Let's call them like A and B.
You don't want to just do like R2 and R3?
I could, but I wanted to write up here the roots. Okay. So I didn't want to just write R2. Or R2 is equal to something. I was like, okay, I'll just do A. So do you mind if we do A and B?
Can we choose like M and N or something? Something that we haven't thought about in terms of our coefficients.
Yeah.
Okay.
What's that going to be?
So the sum, that was the second term, right? So that was going to be negative B over A. So negative 7 over 1, which is 7.
Okay.
So then we have M plus N equals 3. If we simplify that a little bit.
Okay.
And I have a feeling that we're going to have some sort of system of equations.
Can you get me another? Are there more than one Vieta's formulas?
Yes.
So what's the? I'll let you go.
So we also have like the product of all of our roots. So 4mn equals 64 with a positive.
Wait, negative 1 to the 3, right?
Oh, negative. Yes, respect the parity.
Respect the parity. Divided by?
1.
1. Oh, that's nice.
So then M
N is equal to?
Negative 1.
16th, right?
Yeah.
32, 64. Yep. Negative 16th. This kind of looks like an optimization problem. It's not, but we've solved system of equations where there is a product and a sum before. What did you do last time?
We substituted something in to the other one to solve it.
It's like, and let's just like be like n is equal to 3 minus m.
Okay.
Plug it in.
M times 3 minus m equals negative 16. 3m minus m squared equals negative 16. I guess I just want to like move that 16 over.
That's not a problem. I'm gonna rewrite it as negative m squared plus 3m.
You want to leave it in the wonky order?
No, I did not. Okay.
I think it's a 3m, not an n.
Thank you.
Okay. So now what do we need? Like 16, is that factorable?
I'm going to get rid of that negative. Is that cool?
That's fine.
16. Is it factorable?
16
It'd be kind of cool if it wasn't. And I have a, What can we check to know if it's factorable?
Oh, there was that thing. What was it
Call
called?
back.
It's discriminant.
Discriminant?
Discriminant.
So negative b, 3. So not negative b. The discriminant is just the thing under the square root. B squared, 9, minus 4, 1, c. 64 plus 9. 9 minus negative 64. 73.
64. 73.
73. The discriminant 73. That is not a ratio between perfect squares.
Nope.
So this is irrational. Our roots are going to be, well, the m root. M was our second root. The second root is going to be, just we need to get the roots. Negative b plus or minus squared or 4 minus whatever it is. You sing it. I don't. What's it going to be?
9.
Oh, let me, right here. 9 plus or minus.
Root 73, because we did that already.
Yeah, we already did that math. Divided by
2.
2.
But if m is 9 plus or minus that, we also know that our irrational roots come in conjugate pairs.
Yeah, so if like,
n.
Let's just say that m is going to be that one. N needs to be the other one. I think we're done now.
Boom.
I guess I shouldn't get rid of those. I'll just say is equal to, I've already forgotten what it is. I think it's 973. 9 plus root 73 over 2 and 9 minus root 73 over 2. We're done. We don't have to like figure out the other one because it comes in pairs. We have 3 roots.
Nice.
No more, no less. Let's take a peek at the other ones and see if it's kind of, So let's talk this one out, but let's not do it for them.
We got an irrational root.
Irrational root comes in pairs. Yeah. Implicitly, we're being told negative 3 minus root 7 is a root. So then you just need to do something to get the third root, whatever that might be. Let's leave it like that.
An easy Vieta's formula. Like maybe not the third one. Well, that's another irrational root.
Cool.
Lovely. So
It's 2
that comes in
plus
conjugate pair. 2 plus root
All right.
2.
Okay. So now we have 2 roots. How many roots are there in this one?
Oh, did we talk about the fundamental theorem of algebra?
No, we did not. We did not. I think this is a good time to talk about that. The fundamental theorem of algebra. Now, we can't really talk about this in its entirety because we haven't talked about complex numbers yet. But if you guys want to for a journal, look up complex numbers, complex roots. But the fundamental theorem of algebra, what do you know it to be?
I think that is when we have a polynomial, we know that we're going to have a certain number of solutions. And the number of solutions that we're going to have is exactly equal to our degree of our polynomial. As long as, we allow for multiplicity to count as like an additional solution or root.
And I will spoil something for Mr. Rose. So Mr. Rose, if you're watching this, sorry. But when you guys get to Mr. Rose's class, you're going to be using the fundamental theorem of algebra, not calculus, the fundamental theorem of algebra a ton in figuring out what the roots of polynomials are that are much more difficult than what we're dealing with here. We're simply looking at rational coefficients and real roots. But once we've talked about complex numbers, you go off to Precalc C. You'll use the fact that you have complex roots. You'll have the irrational roots. You'll have all these different things, and you'll be able to really visualize polynomials really well with all of these little bits and pieces. So that's the fundamental theorem of algebra. And we have 2 minus root 2 and 2 plus root 2. How many roots are left?
2.
2. And then I think that they can just, we did a problem where we needed to find 2 roots. Maybe it's just the same thing.
I think so.
Maybe we throw these 2 problems on the problem set and we can see if they can do it. What are your thoughts about that?
That sounds like a great idea.
Let's do that. All right, but we'll close this out because we don't want the video to run too long. And we're getting there. It's getting kind of long. How do you want to close this one out? Also, can you hear the lawnmower out there?
No, because I had my own car with a muffler broken.
Oh, I didn't hear it.
Yeah. Oh, right on.
Sweet. How do you want to close this one out?
What was your favorite thing that you did yesterday?
What was my favorite thing that I did yesterday?
The day before National Candy Day.
The day before National Candy Day? Well, I had some candy yesterday in preparation for National Candy Day. I had a regular Reese's, not Reese's Pieces. Went for a run. It was a really good run. Nice. And it's not making me feel guilty about the candy. Kids don't have to worry about eating candy. They have metabolisms. But we're getting to that point in our lives where we don't have metabolisms anymore. So I went for a run and I ate candy.
But they're slow.
We haven't lost it. How about yourself?
I learned how to change the battery in my car.
Nice.
My husband taught me how to do that.
Can I tell a quick story and then we'll close it out? It has to do with what you just said. So I had to learn how to change my battery in my car. And I did it, put it back, linked it all back up. And a couple weeks later, the candy's getting to me. A couple weeks later, I was driving down back from Annapolis. And while I was going 60 miles per hour on the road, my car just shuts off. Lights go out, battery turns off. I no longer have control of my car. And I'm like, what do I do? My power steering is gone. I'm just going down the highway with no control. And then 5 seconds later, after I'm like freaking out, the battery turns back on. The lights go back on. The engine turns back on, and I have control again. I immediately pull over and called AAA. But I put the battery in back incorrectly. Oh. I think it was either that or the battery was just dying, and I needed to get a new one. I ultimately got a new battery, but it was one of the most scary moments in my life. Going 60 miles per hour down on a highway with no control.
Yeah, that's very scary.
Well, so hopefully you put your battery back, not to scare you.
I mean, it worked fine yesterday. I went to the library. I borrowed a ladder from the DIY center at the library. It's fantastic.
The library is the best.
I love the library.
I feel like people don't take advantage of it as much as they once did. Because everything's so digital. Go to the library.
All right.
All right, there we go. Let's do this.
Oh, wait, we have to stop the screen share.
You're right. Oh, good catch.
It takes like 10 times.